So oxidation numbers are a way of accounting, of keeping track of where the electrons have gone, and that's important because all chemical reactions are basically just the transfer of electrons between chemicals. And so oxidation numbers are written with the charge written in front of the number, as opposed to what you're used to when you've been writing the charge after the number. So +2 or -2 is a oxidation number, 2 minus is the charge on the ion. Often they're the same things. So oxidation states and oxidation numbers often get mixed up. So because they're the same thing in this case, so if that's the oxidation state of iron is 2, and so iron has a 2+ charge. It also is the oxidation state, especially if it's just that in its form, which moves us on to the different rules for working out what the oxidation numbers are. So these are the rules. So if an element is by itself and has no charge at 0, on the same account, whatever it is by itself, it has a charge of that. So you'll have iron by itself will have an oxidation of 0, but if it's an iron 2+ charge, it'll have a +2 charge. And so things like nitrogen will have 0. It's a free element without about becoming an anion or a cation. And this another one is the sum of all the oxidation numbers of all the atoms in a species must be equal to the net charge of the species. So we had SO4 2- back there, so we could just have NO3-. Until when you're adding all these up, it must come to an overall negative charge. Basically, the charge on the ion is usually also the oxidation number as well, and so the Group 1 metals are all +1, halogens -1, which is down here. Basically, this just given you down here. They're basically just giving you some general rules. And so, as I mentioned before, the oxidation state and the oxidation number is the same for the transition metals. Generally, if you're not sure what to do, you always put a +2 because all transition metals are also +2, but these are also group 2, so they're normally +2 anyway. The big thing to note is the 2 exceptions, which they like throwing into equations. So metal hydrides are -1, and that's because group 1 metals are more reactive, and so one of them wants to give off. They both want to give off and become a plus, but the group 1 metals are more reactive, so they're more able to give off in the tug of war of who gets the electrons, who takes and who gives. And H2O is hydrogen peroxide is a special case also. Normally oxygen is a -2, so it's a 2- a -2 charge because it becomes a 2- as an ion, and that's because it's normally bound to 2, but in this particular case there's only one particular case where this hydrogen is attracted to it, so you can only steal 1 electron from that, rather than like in H2O where it's stealing 1 electron from one hydrogen, 1 electron from the other, so it's got a 2- overall. So in H2O2 it's actually just 1-, so that's another exception, 0.6 and 7. So I've just added this extra slide in because students are getting things wrong. I think their setting out isn't good enough. So just for example, for sodium sulfate, what I ask you to do, sometimes people are not recognizing their salts, and so they're polyatomic ions, so that there is an actual 2- charge on this. So this polyatomic ion has to have an overall charge of 2-. And so for setting out, you just go down your oxidation number rules table, and for this one, oxygen's the ones that come up first, so that's always -2. And so I asked on the bottom to put the totals. So there's 4 oxygens, so that's -8. Now, you must get an overall charge of -2, and so the sulfur, this bit can only be +6, so there's still a -2 left overall. There's only 1 sulfur, so that gets a +6 overall. And so for the charges to balance off, the other extra 2 has to come from here. And there's 2 sodiums, so there's +1 from each of the sodiums. All right, so do the oxidation numbers on top and the totals on the bottom. It's a good way to set it out so you get it right. All right, so let's do some practice. So here we go. O is by itself, so it must be 0. This one's got 2-, so it must be -2. These ones are a little bit harder. You always go for the oxygens are pretty much always -2, and the hydrogens are always +1. And so you can see that for all of these ones we get the clue from the oxygen and the hydrogen, and you can see that here. Then we just have to work out what's on the other side. So if there's 2 of these oxygens, that'll add up to a total of -4. So to make this neutral, the sulfur must be the opposite of that. So it must be +4. If we go to the ammonia here, again, there's 3+, so this must be 3- for it to balance up. Just look for something a little bit trickier. Here we go, one with a charge. And so you've got +4 here, but there's an overall charge of +1, so you only need a -3 to take from that +4 in order to give it a +1 overall, so the nitrogen's -3. There are also other tricky ones. This one here is a slightly trickier one as well. So -14 is the total. We only want -14 is the total, so we want +14, but there's 2 of them, and so each of those chlorines must contribute 7 each to give us a negative. And there's a nasty one there as well. Just do the bottom one as well. So the oxygens, there's 6 of them, so there's a total of -12. Overall there's a -2 charge, and so we really only want a +10, and we have 4 of them to give +10, so they give an average of 2.5 each. And so that's unusual because you've got an oxidation number that isn't a whole number.